Unions, intersections, and complements in probability. You should be familiar with counting methods such as the general counting principle, permutations, and combinations. It is also useful to know the binomial theorem. You should also be familiar with the basic definitions and terms of probability. In this lesson, we will calculate probabilities of events combined using the conjunctions and, or, and not. The first idea is the union of two events combined using the word or. It is easiest to calculate the probability if the two events are mutually exclusive, meaning that the two events can't happen at the same time. For example, when rolling two dice, you can't get both a total of 7 and a total of 11 at the same time. You can get one or the other, but not both. To get the total probability, we find the probabilities of the individual events separately, then add them together. Here is a visual of the situation. There are 6 occurrences of a total of 7, shaded in pink, and 2 occurrences of a total of 11, shaded sky blue, for a total of 8 possibilities out of 36. We merely add the pink and blue boxes together. Formally, the probability of E or F is the probability of E plus the probability of F. One thing that can complicate the situation is when one event influences the probability of another. For example, you are playing a game which you will win if you roll at least 10 on 2 dice. The probability of that event, event F, is 6 out of 36. There are 3 ways to roll 10, 2 ways to roll 11, and 1 way to roll 12. When we learn of the outcome of one of the 2 dice, the blue die, we change our estimate of the likelihood. Now that we know that the blue die landed 6, the probability of the event F has increased. We call this conditional probability. What is the probability of F conditioned on the fact that event E happened? In this case, the probability of event F getting a total of 10 now becomes a question of what happens on the second die. We already have 6, we just need 4 more, so 3 of the 6 possibilities are good. The probability of F, given that E happened, is 3/6, much better than the original 6 out of 36. Here's another look at the last example. The probability of getting a total of at least 10 when rolling 2 dice is 6 out of 36. Once we learn that the blue die landed 6, we only have 6 remaining possibilities, 3 of which give a total of at least 10. Sometimes E and F have nothing to do with one another. What did we roll on the red die? If I tell you that the blue die was 6, it gives us no information relevant to the red die. The probabilities don't change for the red die. If the probability of F given E is the same as it was without knowing E, then E and F are said to be independent. In terms of the two-dimensional grid, this means that all of the columns contain information that is consistent, not depending on the rows. When 2 events are independent, we can calculate the probability of 2 events both happening. For example, when rolling 2 dice, what is the probability that both are 5? The key word here is and. What is the probability that the blue die is 5 and the red die is 5? We see here the 1 row that the outcome must be in and the 1 column that the outcome must be in, giving us 1 success in 36 chances. Formally, when combining probabilities of independent events using and, we can find the probability of both by multiplying. This can be seen by the general counting principle. To compute the denominator, we find the total possibilities by computing the area of the large rectangle. To find the numerator, we multiply the number of ways that E can occur by the number of ways that F can occur. This is the area of the darkest gray rectangle, once again found via the general counting principle by multiplying. This is the same procedure we use to multiply fractions. The last word we need to understand is not. We simply need to find the portion that is excluded. If there's a 40% chance of rain today, the remainder, 60% of the time, it won't rain. We are now ready for a slightly more detailed formula for unions of independent events. When rolling 2 dice, what is the probability of getting a 5 on at least one of the 2? This can be read using the word or. We need to get a 5 on the blue die or a 5 on the red die. There are 6 outcomes in the blue row. There are 6 outcomes in the red column, but we have overcounted. When both dice are 5, we counted it in the blue row and in the red column. We need to adjust for this by subtracting the double counting, the intersection. The correct answer is to add the probabilities of E and F, then subtract the overlap. If E and F are mutually exclusive, then there is no overlap, and we have our original formula. Here are some examples. You may wish to pause the video to see if you can find these probabilities. There are 4 suits, so 1/4 of the cards are spades and 1/4 of the cards are clubs. Since these are mutually exclusive, the word or means add, so we get 2/4. There are 13 possible values, of which 7 is one of them. There are 4 possible suits, of which hearts is one of them. The word and means multiply, so we get the probability 1 out of 52. This makes sense because the 7 of hearts is one of the 52 cards in a deck. There are 13 ranks, of which king is one of the 13, so the other 12 ranks are not king. In the last example, we need to account for the overlap. There are 4 sevens and 13 spades, which makes 17 possibilities. But we counted the 7 of spades twice, so we subtract the overlap to get 16 out of 52. To recap, to combine probabilities using and, we multiply the probabilities. The phrase both E and F means E and F. To combine probabilities using or, we add the probabilities, subtracting the overlap if they are not mutually exclusive. The word not finds the remaining probability so that the 2 parts add to 100%.